the last class we derived the planar mobility criterion, and then Grubler's criterion is nothing but the mobility criterion for mechanisms with mobility equal to 1 and only single degree of freedom joints. It is just a special case of the planar mobility criterion. And the first thing that we saw from Grubler's criterion is that since this number is an even number, n has to be even. So, if you want to create a mechanism with mobility equal to 1, you need an even number of links. Okay. So, that is the first observation that we have from this. Okay. Now, let us look at some applications of Grubler's criterion, because we looked at, so the first application is what is the minimum number of binary links we need. Okay. And for this we go back to the form of the criterion. So, we say n is equal to, what did we have there? It is a closed chain, so no singular links. You have n2 plus n3 plus a link of order I. Okay. Order I meaning it has I nodes. Okay. So, we have that is your total number of links, and then I can say that 2j1 equals 2n2 plus 3n3 plus so on up to I n I. Okay. Remember that this applies only when you are dealing with simple hinge joints. So, you have to be very careful if you are trying to find the mobility of a mechanism using this kind of an approach. Okay. So, otherwise you could go wrong, because in many real life mechanisms you would have joints that have multiple links connected. You would have a hinge joint, a compound hinge joint. Okay. So, you would not have where you have to count multiple joints. So, do not use this unless you ensure that all the links have only simple hinge joints, are connected by only simple hinge joints. Okay. So, for m equal to 1, we can with only simple hinge joints, I can write this as (3n minus), so 3n minus 2j1 minus 4 equal to 0, right. That is my Grubler's criterion becomes 3 into n2 plus n3 plus so on up to n I minus 2n2 plus 3n3 plus I n I minus 4 equal to 0. Okay. So, now what happens? I can write this as, if I 3n2 minus 2n2, so I get n2, okay, and if I take the other things to the other side, 3n3, 3n3, all the ternary links are out of this equation. So, I get sigma p equal to 4 to I p minus 3 n p plus 4. Okay. So, p equal to 4 to I meaning links of order 4 and above. So, couple of things I see from here. From here, what does this tell me about the minimum number of binary links I need to create a single degree of freedom mechanism? Minimum number of links I need is 4. So, minimum number of binary links needed equals 4, which is why your 4 bar is the simplest mechanism with mobility equal to 1. Okay. So, that is the first observation. The second observation is the mobility equation in this form is independent of the number of ternary links, because the ternary links went out of the equation. So, the mobility is independent subject to certain conditions, independent of the number of ternary links. Why do I say subject to certain conditions? If I add one ternary link, okay, how many joints does it add to the mechanism? Each ternary link adds how many J1s? No, in the equation you get 3 by 2, each one is shared with. So, if I add one link, I am actually adding 3 by 2 joints to the mechanism. So, I can't have a mechanism with fractional number of joints. So, ternary links have to be added in pairs in this case. Okay. Therefore, ternary links need to be added in pairs. This is still, you will still have to look at the entire mechanism, look at this thing to ensure that, but the addition of ternary links in pairs alone, provided all the other things are met, will not affect the mobility of the mechanism. That is what this equation tells you. Okay. So, if I add ternary links in pairs, then I still get an integer number of joints, and therefore, I should still be able to make a mechanism with mobility equal to 1. So, if you look at a 4 bar to a 6 bar, you will see that. So, I have a 4 bar, I have so this is 1, 2, 3, 4, all simple hinge joints. Which are the 2 ternary links? So, let me 1, 2, 3, 4, 5, 6. Ternary links are 1 and 6. Sorry, 1 and 4. 1 and 4. 1 and 4 are ternary links. The mobility remains unchanged. Mobility of this is also 1. Mobility of this is also 1. Okay. So, this is an example where you add a pair of ternary links and the mobility of the mechanism is not affected. The next thing that we will look at is, okay, so for a link of mobility 1, sorry, for a linkage of mobility 1, what is the highest order link you could have in the mechanism? M equal to 1. So, let us look at it from the, we will approach this problem indirectly. So, what we will say is, okay, I have a link with I nodes. Okay. Let us say, let me just cut this. Okay. This thing will not let me cut it there, erase part of it. So, I will just go with this. Okay. So, let us say I have a link with I nodes. So, I want to find out how many links do I need minimum number. Okay. To achieve closure when one link is connected to I simple hinge joints. Okay. How do I make a mechanism out of this? Basically, I am looking for a closed kinematic chain. If I have one link which has I nodes, what is the minimum number of links I would need in order to achieve a closed chain? So, let us start off with start connecting these to each of the I nodes to links. Okay. So, start from, so I start with 1, 2, 3, 4, this is say I minus 1 I. So, these are the links connected to the I nodes. Okay. Now, first link and ith link I can choose binary links. The reason I choose 2, 3, 4 to be ternary links is so that I will have simple hinge joints when I try to close the kinematic chain. Okay. Now, let me say that okay, I connect. So, then this, this, this and so on. Okay. Here I will have something connected to that, something coming from here. Okay, to form a closed chain. This is my link with I hinges or I nodes. Yeah. So, how many links? Now, count the number of links that I have. I have I links here. Okay. So, then this is I plus 1, this is I plus 2th link. Okay. This link would be I plus 3. Therefore, this link will be I plus I minus 1. Okay. So, what is my total number of links now? N equal to I plus I minus 1, that is the total number of links, plus 1. That gives me N equal to 2I. So, if I have a link with I nodes, I need a minimum of 2I to make a single degree of freedom mechanism. Now, I do not know yet that I have a single degree of freedom mechanism. So, let us check Grubler's criterion. Okay. So, 3n minus 2j1 minus 4 should be equal to 0. So, 3n is 3 into 2i. What is the number of joints that you have? Count the number of joints. What do you get there? 3, yeah, yeah. That would give you 3i minus 2. 3i minus 2, j1 equal to 3i minus 2. So, I get minus 2 into 3i minus 2 minus 4. So, Grubler's criterion is satisfied. So, I do get a single degree of freedom mechanism with these 2i links. Okay. So, that tells me that if I have n links, I max can be what? If I have n links in the mechanism, I max can only be n by 2. The reverse of, right. If I want to use a link with I nodes, I need to have minimum 2i number of links. If I have a mechanism with n links, I max can only be n by 2. Okay. So, going back to my 6 bar, 6 links, the maximum order of a link in a 6 bar can be 3. So, you can't have more a link of a higher order than a ternary link in a 6 bar mechanism. Okay. Similarly, in an 8 bar, if you want a single degree of freedom mechanism, a quaternary link is the maximum order of the link that you can have. Okay. So, this form of the Grubler criterion gives you these additional insights into which we will use when we look at the next application, which is basically number synthesis. So, number synthesis is essentially finding the number of links and the order of the links that you require in order to make a mechanism with a certain mobility. So, this is just okay, what kind of links do I choose? I have a box of links. I want to create a mechanism with certain mobility. How do I choose my combinations of links in order to do that? So, number synthesis is the determination and types meaning order. That is how many nodes each link. Simple pairs to get a single degree of freedom linkage, planar linkage. Here we are looking at so we already have, so we know 3n has to be 2j1 plus 4. Okay. We know n2 should be greater than or equal to 4. We know n has to be even. Right. And we know I max equal to n by 2. Okay. So, what combinations can we have if we want to design say a 6 bar. So, 4 bar is pretty straightforward, because I need to have a minimum number of 4 binary links. Binary is the maximum I can have in a 4 bar, the number of nodes. So, 4 bar is done. Let us look at a 6 bar. Okay. Let us see how. So, the next one is, because n has to be even, n equal to 6. Okay. Mechanism. Now, you may ask, if single degree of freedom is what we want, why not just use a 4 bar all the time? In most cases you do end up using a 4 bar, but in many cases you will also need to augment. You would need more links, because you could get more complex motions. You could get, those of you who have seen before, sometimes if your 4 bar cannot do full rotations, you will need to add a couple more links and make it a 6 bar in order to be able to run it with a motor, etc. So, in many applications 6 bars are quite widely used. You may start off by designing the 4 bar and then make it a 6 bar in order to just even be able to run it with a continuous input. Okay. So, with this we know when mechanism has I equal to 6, sorry, n equal to 6, I max is 6 by 2, 3. Okay. So, what are the options? It has to follow all these conditions. 3n, it has to satisfy, the number of joins have to satisfy the mobility criterion, minimum 4 binary links. So, what are the options? So, I can have n2 and n3, let us say. Okay. No n4 is possible. So, I have n2, n3, what do I get? My possibilities are, I can have 4 n2, that is the minimum number I need. I can have 2 n3. So, calculate J1. Calculate mobility. The other option is, again n has to be even. So, n2 can be 6, n3 can be 0. Those are my only 2 possibilities. Yeah, write the equation. So, what do you have for J? You get J1 equal to 7 here, you get m equal to 1 here, you get J1 equal to, okay, you can just solve simultaneously and then you will find that this is the only solution basically. I think here you get J1 equal to 6 and mobility equal to 3. So, this will not be an option. Okay. So, your only option for a 6 bar is 4 binary links, 2 ternary links. Okay. And that is how you get the 2 configurations of the 6 bar, which you have seen before. One is the, do you remember? Anybody? So, you have 2 ternary links. This is the Watts configuration. Watts configuration, the 2 ternary links are directly connected to one another. That is one way to remember. Direct connection between the 2 ternary links in the Watts chain. In the Stephenson chain, the other chain is the they are separated by a binary link. The chain itself is called the Watts chain or the Stephenson chain. Depending on which link you fix, you can this could be fixed or any of the others could be fixed, as we will see when we come to inversions. So, Stephenson's chain, the two ternary links are separated by a binary link. So, you have again 1, 2, 3, 4, 5, 6. Again J1 will be 7 in both of them, mobility equal to 1. You can also think of the Watts as 2 4 bars, one 4 bar chain. The output of one 4 bar provides the input to the other 4 bar. So, one 4 bar driving another is a Watts chain, which is what you will commonly use when you do the driver diode synthesis. Again here 5 is not, we could have tried 5 and 1, but again that is not possible because J1 will be, ternary links have to be in pairs again. So, this is also not a possibility because you will get a fractional J1 in this case. Now, let us look at the next n equal to 8. Let us do one more, see what options you get. So, again I max is here 4 for n equal to 8. So, I can have n2, n3, n4, 4, 2 and or 4 4 0, let us say 6, 2 0, 6 0 2 combinations. Which ones are possibilities? So, you are basically solving n2 plus n3 plus n4 equal to 8, subject to these conditions, and J1 should satisfy Grubler's criterion. Can have n2 5, 2 n3 1 n4 possibly. So, tell me what are the possibilities. This one is possible, 602 is possible. Okay. So, this is how you would do the number synthesis, that would be the first step. 5 to 1 is also possible. So, this is an example of number synthesis. So, the numbers and possibilities grow very rapidly once the number of links grows. Okay. So, the options become very many. In many cases you do not really look at, and in many cases also you are actually doing it as building blocks. You take a 4 bar, then maybe you add 2 more links to drive it, or add another parallelogram mechanism to it to make an 8 bar, etc. So, the mechanisms that you will encounter in real life can typically be broken down into smaller units. You will see that even though overall if you count the number of links, it will be an 8. It is very rarely that you say, okay, I want to design an 8 bar, and you go about doing it this way. Okay. Now, once you get this, so this is for everything having simple hinge joints, okay. But you can sort of modify, you can shrink links, or make nodes collapse, and that will sometimes change the mobility, or it will keep the mobility the same. So, an example of something where you collapse a joint, okay. So, this is your Watt's chain, right. I could collapse these two joints, bring them together. Actually, that is not okay, and do this. Same thing, only thing when I am calculating the mobility, I have to make sure that I calculate 2 J1s here. So, I collapse the joint, it did not change the mobility of the mechanism. Okay. So, so basically I coalesced the joints. Okay. So, coalesce, did I get the spelling right? And M remains the same. Okay. If I completely shrink a joint, okay, then I mean if I take this entire link off and directly connect this, then what happens? It is essentially removing the link. So, what happens to my mobility? Here mobility becomes 0. So, complete shrinkage, mobility becomes, this link is shrunk, right. So, from mobility you lose mobility. Okay. So, here mobility equal to 0. Complete shrinkage leads to reduction in the mobility by 1. So, this is basically complete shrinkage implies removal of a link. So, if any ternary or higher order link can be partially shrunk, and to a lower order link, which will result in multiple joints, but will not change the mobility. Okay. So, that is the case here. Okay. Okay. So, the next topic, so this kind of concludes the mobility equation and some applications of it and how you use it for number synthesis. Okay. So, now once we have a mechanism, we look at the concept of inversion. You would have all seen this already. Essentially, when you have a closed kinematic chain, if you fix a different link in the kinematic chain, the relative motion between the links does not change, but if you look at the motion with respect to the fixed link, it will be different. Okay, but the relative motion among the links does not change. So, an inversion is basically, so if you have a 4 bar linkage, my possibilities are 4 inversions, because I could fix a different link in the kinematic chain each time. The inversions could be what are known as distinct inversions or non-distinct inversions. As many inversions as there are links. Inversions may be distinct or non-distinct. We will see what that means. And for a 4 bar or a 4R, okay, 4R, 4 revolute joints, typically a 4 bar is referred to as 4R mechanism. A slider crank, as I mentioned earlier, would be a 3R 1P mechanism. So, the Grashof criterion is a geometric criterion that gives the range of motion for a 4 bar mechanism. So, if you have the 4 links and you classify them as the shortest link, longest link, and the other 2 links you call them P and Q, then if S plus L is less than P plus Q, then it is called a Grashof mechanism, or some literature refers to it as Grashof type 1. If it satisfies the Grashof criterion, it is Grashof type 1, and then at least one link. So, it tells you that at least one link is capable of a complete rotation. If S plus L is greater than P plus Q, then it is called a non-Grashof or Grashof type 2. A non-Grashof is also called a Grashof type 2, and the special case where S plus L equal to P plus Q is called a Grashof neutral. Mechanism, Grashof neutral linkage. And for this you only need the link lengths. You do not even have to put the mechanism together. The Grashof criterion tells you that with a certain set of links, with the link lengths, you can predict whether any of the links in the mechanism is capable of making a complete rotation. And then depending on which inversion you are looking at, the nature of motion of the links will change. Okay. The relative motion always remains the same. So, but if I fix a different link in the kinematic chain, I get a different behavior with respect to the absolute frame. So, in all these you can see that the relative configurations of the link is the same, right. If the link next to the, so the green link here is the shortest link, okay. The link lengths are chosen here such that it is a Grashof type 1 mechanism, and if the link next to the shortest link is fixed, okay, then the shortest link is capable of, in all cases the shortest link is the one that is capable of the full rotation. Here you can see that the shortest link makes a complete rotation, the green link, and the other two links kind of go back and forth between two limits. Okay, so you can see the blue rocker, the limits of motion of that rocker. Okay. So, this is called a crank rocker, okay, or it's called a Grashof crank rocker, okay, which means this first link. So, you have a fixed link, the link next to the fixed link is your crank, makes the complete rotation, the other two are rockers. In the case of this one, so next to the shortest link I have the red link or the orange link. If I fix the orange link, now again the green link makes a complete rotation, the blue link rocks between limits, okay, it is not able to undergo a complete rotation. So, these two still give me crank rockers, either side of the shortest link if I fix, I get crank rockers. So, they are called non-distinct inversions, because the nature of the inversion is non-distinct. Although the net, if you look at the output motion, the rocker here moves, this is the motion of the rocker, here this is the motion of the rocker, but they are still called non-distinct inversions. Okay. So, this is again Grashof crank rocker, or to distinguish you could say Grashof rocker crank, okay, just to follow the, but it is better to say this because that way you know it is the link next to the shortest link is fixed. So, this is also a GCRR. The third inversion where your blue link, sorry, the shortest link itself is fixed. Okay. In this case you will find that all three links can make complete rotations. You can see even the coupler is tumbling. So, this is a case of Grashof crank. This inversion where the shortest link is fixed. And the fourth one where you have the link opposite the shortest link is fixed, you will see that it is the coupler that is doing a tumbling in the plane. Okay. It is not rotation about a fixed point, but it is undergoing a complete revolution. So, it is called a tumbling coupler. So, this is this is the link opposite the fixed link. So, you have the Grashof rocker crank rocker. Okay. So, here link, both of these link adjacent to the fixed link, sorry, adjacent to the shortest link is fixed. These are non-distinct inversions. This one GCCC, the shortest link is fixed. And here the link opposite to the shortest link is fixed. So, this is the case with the tumbling coupler. Do you have a question? Why is it the case that? So, it does not say you can connect the shortest and the longest together. Grashof does not say how you have to connect the links. It only says, so you could have, it does not talk about, so you could have many more options. Here if you have a certain kinematic chain, the same things apply regardless of which link you put next to which link in terms of the dimensions of the link. So, just by knowing the dimensions alone, the Grashof criterion tells you how it is actually based, if you look at the proof of it, it is just based on the triangle inequality. You look at the extreme, you look at the positions, the sum of two sides of a triangle should be greater than the sum of the third side, or the sum of a side of a triangle should be less than the sum of the other two sides. That is basically what the proof of this is based on. And there you will find out that the shortest link is the one that will make the complete revolution. Okay. But other than that, you can attach the links, you can attach the longest link next to the shortest link, there is no problem with that. I picked certain dimensions in order to be able to show, in some you may not see the tumbling coupler very clearly, for instance. Okay.